Welcome back. In the sessions so far, we've talked about a single data variable, how to compute its measure of centrality, dispersion, skewness, fitting a distribution. In this session, I want to change the focus to looking at two data variables and looking to see if there are relationships between those two variables. So if I gave you two or more data series, price earnings ratios and interest rates, earnings and growth, you can check for linkages in the data statistically and see whether they move together, move in different directions inversely, or are unrelated. Now, if there is a linkage, you can explore further. You can explore to see if there are any time lags or leads. In other words, does one variable happen first and the other follows, or vice versa? You can also check to see whether the correlation amounts to causation. You're saying, what's the difference? When two variables move together, there's correlation. Statistically, that's always the case. If I ask you, is one variable causing the other? That's a different question. That requires further tests. So sometimes, and this is something you learn in statistics all the time, you can see two variables that are correlated, but there is no causation. One doesn't cause the other. And third, and this is where it comes into use in investing and finance, if there is a linkage between two variables, perhaps, you can use one to predict the other. And since this is investing, try to make money on it. So let's get this process rolling. Whenever you have two variables, let's start with two first. The best place to see if they have a linkage or a relationship is to do what's called a scatter plot. What's a scatter plot? You take two variables. For purposes of generality, let's call the variables y and x. And let's say you have 10 observations on each one at different points in time. So day 1, day 2, day 3, you observe y and x. So they work in pairs. You take each pair. So on day 1, if the numbers you got for y were 1 and the number for x is 14, you plot that point. So this is basically a scatter plot. Each observation or pair of observations is plotted on the graph. Now, there's no reason you need to stick with this, but in statistics usually, if you look at the y-axis, it's the y variable, and the x-axis basically. So the x is often called the independent variable, y is called the dependent variable, but we'll hold off on that. This is just a scatter plot of y and x. Now, y and x are abstractions, but you can say it could be price earnings and growth. It could be earnings growth at companies and GDP growth. It could be any two variables. Of course, when I look at those two, I get a sense that they move together and in inverse directions, right? Just looking at the graph. But that's just visual checking. So here's one way to see how two variables move together. You can compute what's called a correlation coefficient. There are various measures of correlation coefficients, but the most widely used one is called the Pearson correlation coefficient. I'll give you the intuition as to what it does, and then of course you'd probably use a statistics package or Excel to do it. What we do in the Pearson correlation coefficient is we take each observation, we look at how y is different from the average of y and x is different. So in each one, I'm looking at the deviation of that observation from the mean for each of my two variables and then looking to see whether they're moving together. So if we have two variables that move together, when one is higher than the average, so y, the observation is higher than the average y, the x observation will also be likely to be higher than x. If they move in inverse directions, when y is higher than the average for y, the x will be lower than the average for x. And I sum up this across all my observations. Now, if I work through the statistics, I'll come up with a correlation coefficient. A correlation coefficient is standardized. What does that mean? No matter what the data looks like, when I'm done, the correlation coefficient will always lie between -1 and +1. When I have a +1 correlation coefficient, I have two variables that move in lockstep together, up and down. When I have a correlation of -1, I have two variables that move in lockstep but in opposite directions. When one goes up, the other goes down in exact proportionality. When I have a correlation coefficient of 0, there's no relationship. The way the two move have nothing to do with each other. And of course, if you have positive correlation coefficients, you have two variables that move together. You have negative correlation coefficients, they move in opposite directions. So one standard measure of two variables moving together is a correlation coefficient. There's a second measure of co-movement called the covariance. The covariance actually starts in the same place as the correlation coefficient. It looks at the deviation of each observation from the average and looks to see whether they move together. But the only difference is it's not standardized. In other words, if you have a positive correlation, you're going to get a positive covariance. A zero correlation, you get a zero covariance. And a negative covariance, you get a negative correlation, you get a negative covariance. But the difference is the covariance is not bounded between -1 and +1. So what is it going to be? It's going to depend on the levels of the variables. So if I took IBM stock price and stock returns and looked at how they move with the market, I could tell you that the correlation between the two is 0.22. That already tells you everything you need to know about what I found in IBM. It moves with the market, the correlation is positive, but it's not big. It's not a hugely positive number. But if I told you the covariance between IBM stock returns and the market is 37%, you can see already why covariances are tougher to read. Your reaction is going to be, is 37% a high number, a low number, an average number? That's the limitation of covariance. It's not in units that you can immediately jump on, but it conveys the same information as correlation. So let's see where we are. You have two variables. You can check to see whether they move together with a scatter plot visually, and then you can compute the correlation and the covariance. But let's go back to the scatter plot. Because when you look at two variables and you do find a correlation, it's worth being a little cautious about jumping to conclusions. You can have two variables move together, and while you might be tempted to tell all kinds of big stories about why they move together, a lot of correlations are pure chance. Now, in finance, we have a problem. You know what our problem is? We have too much data on too many variables, thousands of variables going back 100 years. If you have thousands of variables going back 100 years and you start computing the correlation between every pair, well, guess what? You're going to find some variables look like they move together when there's really no reason why they need to. I'll give you one of my most favorite or least favorite examples of this. There is this story that stock market returns are driven by who wins the Super Bowl. For those of you who are not familiar with the NFL, the Super Bowl is played between an AFC team and an NFC team. And there are these studies that go back 55 years and show that if an NFC team wins the Super Bowl, stocks do well, and if an AFC team wins the Super Bowl, stocks do badly. Correlation is right there. You're saying, well, if the correlation is there, why should I contest it? You know what? I could give you 100 other variables, and my guess is you could find 10 other variables that are correlated to the market for no good reason. So when you see correlation between two variables, it's good to bring common sense to play and say, should there be a linkage? And if so, let's dig deeper. Second, just because you find a correlation between two variables doesn't imply causation. In other words, you can't assume one causes the other. That requires more testing, more data might need to be collected. I'll give you one very simple example. If you took the wealth levels of households and you look at the percentage of their food bill that they spend on organic food, there's probably a high positive correlation. I'll confess I haven't tested this, but my guess is there's a high positive correlation. You're saying, so what? If you then take that correlation and say, well, if you buy a lot of organic food, you will get rich. You see why that's absurd? That correlation doesn't work. That correlation doesn't translate into causation. In fact, if you expected causation and you brought common sense to play, you're going to say, being rich gives you the discretionary income to buy organic food. It's being rich that drives the organic food buying, not the other way around. It's pretty obvious in that case, but this is the kind of challenge you can often face when you're correlation asking, hey, which direction does the causation run? And finally, the reality is that to run these correlations and covariances, you need data. At the risk of stating the obvious, your data is always from the past. You're saying, so what? Well, unfortunately, our predictions have to be about the future because our actions are in the future. This is always the case when you're making predictions based on past data. But I think it's worth remembering, when I use past data to make a prediction, I am also assuming that the future is going to look like the past, and that could be dangerous if your correlations are shifting over time. So with that set up, let's go back to the scatter plot. If I take that scatter plot that I just showed you, and this is the same scatter plot, and I fit a line, it's called the best fit line, through that scatter plot. It's the red line. Your first reaction is, how the heck do you find that line? Well, I could eyeball the data and do it, but that wouldn't be very statistical or scientific, right? The most common type of regression is called ordinary least squared regression, OLS. You're saying, what does that mean? In OLS regression, the way you fit a line is you look to minimize the square distances of the points from the line. Let me repeat that again. In ordinary least squared regression, you're trying to minimize the square distances. In the old days, before computers and calculators, you know what people used to do? They used to measure the distance of each point from the line, take the square distances, add them up, and see what minimized it. It was a lot more work. Thank God we live in 2020. Statistics packages will now fit this line for you, but that's what they're doing. They minimize the least square differences. Now let's take a look at the regression and see if we can deconstruct the output. First, let's start with the slope of the line. The slope here is negative. In fact, the coefficient on the slope is minus 1.1. For every movement of 1 in the x variable, the y variable drops by 1.1. So it's a negative slope. It's a downward sloping regression line. The y variable and the x variable move in opposite directions. You know what? If you compute a correlation between y and x, guess what kind of correlation you're going to get? You're going to get a negative correlation. Minus 1.1 is the slope. You're saying, what's the 14? That's called the intercept. The intuitive way to think about the intercept is it's the value that your y variable will take if x is 0. So let me repeat that again. If your x variable is 0, the intercept is what the y variable will be. Now that regression line is basically the numbers that capture your best fit line. Now there's one final statistic you will see in almost every regression. It's called the R-squared. What's the R-squared? The R-squared is a measure of how good your line is in fitting the data. We start with an extreme. If you have a perfect fit line, every point was on the line, you know what your R-squared is going to be? 100%. This case, you can see the R-squared is high, but it's not 100%. It might be 60, 70, 75%. You don't throw away the regression because you don't have a perfect regression. Now, once in a while, you might do a scatter plot and fit a line, and you might get a horizontal line. You know what that tells you? There's no relationship between your y and your x variable. Your R-squared is going to be 0. So scatter plots, correlations, covariances, best fit lines are all part of the same discussion. You're looking at two variables, you're trying to see whether the two move together, and with the best fit line, you're trying to go further. Can I use one variable to get an expected value for the other? In this case, the answer is yes. So far our discussion has been about two variables, but what if you have three variables? If you are using correlations, you know what you need to do, right? You have to look at every pair. So you have three variables, A, B, and C. You have to look at the correlation between A and B and C, and A and C, and B and C. You're saying, why can't I do a correlation across A, B, and C? It doesn't work that way. Correlations are across pairs of variables. But if you have three variables or more, here are some of the things you can do. You can try to do a scatter plot, but it gets really messy. Even with three variables, and once you get past three, it gets really, really, really messy. I'll show you the three-dimensional plot you can do with three variables. I'll let you think about four-dimensional plots and how to get them. And with regressions, the ordinary least squared regression that I talked about, two variables, you can extend that to what are called multiple regressions. You still have only one dependent variable, but you have many independent variables. How many? As many as you want, as long as you have the data. So let's look at a scatter plot, a three-dimensional plot. A three-dimensional plot, here's what you do. You have three variables, you have three numbers for each observation, right? You look to plot a point for those three numbers. You do that for every observation. So each one is a plotting of 3 points. So your if you're going to call A, B, and C, each point is an observation. That's a scatter plot. It's a three-dimensional scatter plot. You can create these in Excel. You can create these in most statistics packages. I'll make a confession. I struggle with three-dimensional plots. I don't know whether I'm coming or going, I'm jumping, I'm climbing a mountain or falling down into a valley. But if you want to show it as a picture, that's what a three-dimensional scatter plot is going to look like. You're saying, how do I fit a best fit line? Hold on, we'll talk about that. But that's a 3D plot. Incidentally, there are interesting ways in which people have gone to four-dimensional plots. In fact, one of the great advances over the last 20 years is in presenting data. So there are very interesting ways in which people have found ways of presenting more than three variables. But let's face it, once you get past two variables, these pictures get more and more difficult to read. Now, incidentally, when you look at these variables, especially when you talk about multiple regression, you have multiple regression, there are a couple of interesting twists on independent variables that you might be able to use, especially when you run into issues. The first are what are called dummy variables. A dummy variable can take on the value of either 0 or 1. You're saying, when would I use something like this? Let's assume you have 50 companies in your sample, 30 are public, 20 are private, and you're looking at something, debt ratio of these companies is a function of earnings. But you worry about the fact that private companies might behave very differently than public companies. So you know what you might do? You might run a regression of debt ratios against earnings and then throw in a dummy variable, which is set to 1 if a company is a private company and 0 if it's a public company. Then your regression, the coefficient on that variable will tell you whether your hypothesis was right, whether private companies behave differently than public companies. So if you have a discrete variable, private versus public is discrete, a dummy variable allows you to do it. In some cases, you might take a variable that's continuous and replace it with a dummy variable. For instance, your cost of debt as a company might be a function of what your default risk is going to be, which is a pretty straightforward thing. And default risk is continuous, right? You can have very little, you can have a little bit more. It's not a discrete variable. But let's say that you find it too messy to bring in default risk as a continuous variable. What you might do is break your companies down based on their bond rating. So, with bond ratings, a rating above BBB, or BBB or above is viewed as investment grade. You might break your companies down into investment grade and non-investment grade and use a dummy variable to capture that difference. So dummy variables. The second is, in some cases, you might worry about two independent variables in your regression that might have that might have cross effects. In other words, how they move together can affect your dependent variable. As an example, think about PE ratios, a number that we use often in investing, and think about a hypothesis that large companies have lower PE ratios than small companies, and that the higher your growth rate is, the higher your PE ratio. And then you say, but I also worry about small companies with high growth rates behave differently than large companies with high growth rates. In other words, it's a cross effect. You can run a multiple regression with PE ratios as a dependent variable, that's what you're trying to explain, growth rate and market cap as independent variables, and then you throw in the product of growth rate and market cap in there as a third independent variable to capture the cross effect. It's a very primitive regression, but you can think of the possibilities here. So let's say you've run a regression, simple or multiple. Before you get ready to use it, there are a few things you might want to check on that regression. The first is traditional, conventional regressions, OLS or multiple regressions, assume linear relationships between your dependent and your independent variable. You're saying, what does that mean? They assume that as your independent variable goes from 1 to 2 to 3 or whatever the levels are, your dependent variable moves proportionately. It's linear. Well, what if it's not? There are two choices. You can run what's called a non-linear regression, and there are many statistics packages that offer this choice. Or you can take your independent variable and do some kind of transformation. Take the log of that variable, the square of that variable, the square root of that variable to make the relationship more linear. We'll look at a couple of examples of this later in the class so that you can see this play out. Nonlinearity. The second is what's called multicollinearity. Remember, in a multiple regression, you have more than one independent variable. You have 2, maybe 3, maybe even 4 independent variables. In a perfect world, these independent variables should be uncorrelated with each other. In other words, how they move should be unrelated in a perfect world. Unfortunately, we don't live in a perfect world. So guess what? In the real world, independent variables tend to be correlated, and that's called multicollinearity. I remember in my statistics class sitting there saying, who cares? Now I do. The third issue you might have to run into regressions is called homoskedasticity. Again, sounds fancy. Statistics people love to create these big words. But here's what it means. When you use your independent variable to predict your dependent variable, you get a prediction, and that prediction will have an error. It's called a residual. And if your regression is good, that error should remain the same as your independent variable goes from low to high. So in other words, as I change my independent variable and look at my prediction mistakes, there should be no pattern. They shouldn't get larger as the independent variable gets larger or smaller. They should basically fall kind of randomly on either side of the line. That's in a good regression. If I violate that rule, then I can have a problem with my regression. And finally, the residuals from your regression, at least in a perfect world, should be normally distributed. Remember in the last session we talked about checking for normal distributions? You might want to do that on the residuals on your regression. So let's talk about linear versus nonlinear regressions. Best way to illustrate this is go back to a scatter plot. Here you have a scatter plot, pretty linear, right? As you can see, even as I fit the line, I'm not worried. This looks pretty linear and positive. Here's linear and negative. But look at this third scatter plot. I could fit a straight line through it, but you can already see it's going to be a bit of a reach. The straight line will not fit because it looks like there is a nonlinear relationship. Again, this is from a visual scan. There are ways in which you can test your data to see if it's nonlinear. And if your regression data has a nonlinear relationship, you can run a nonlinear regression. I'm not going to go deeper than that because I'll make a confession. In all my years of using statistics in finance, I have almost never run a nonlinear regression. Not because I don't have nonlinear relationships in my data, but often I would find it easier to transform the data and make the relationship more linear than actually running a nonlinear regression. One reason nonlinear regressions are trickier is unlike the linear regression where I gave you the rule, minimize the least squared differences, there's an element of trial and error and different ways in which you can fit nonlinearity. Luckily, we have statistics packages, as I said, that do it for you, but it's still much more difficult to read the output. As I said, I prefer to transform variables. You can use trial and error. You can try different transformations, do scatter plots with each one, and see which one gives you the best transformation, the one that offers the most linear relationship. Now we talked about multicollinearity. One of the first things you should always do when you run a multiple regression is take your independent variables and create what's called a correlation matrix, which is basically how do pairs of your independent variables move together. In a perfect regression, that correlation matrix should have 1 in the diagonal. In other words, a variable is obviously related perfectly with itself and 0 on every other cell. But when you open up a correlation matrix for almost any real-world regression, especially in finance and investing, you're going to see correlation numbers that are not 0. You say, what do I do next? Before you freak out, what that multicollinearity does, it affects the precision of the coefficient. Let me give you the intuitive reason why. If you have two independent variables, let's call them y1, x1 and x2, and let's say they correlate with each other, the data gets confused. It doesn't know which variable is measuring what, and the coefficients that you get for x1 and x2 might not reflect how each variable behaves separately. So you've got to be a little more careful about reading the coefficients and the statistical power of those coefficients. Interesting though, even if you have multicollinearity in your regression, the whole regression can still be used in predictions. It doesn't affect the predictions of precision, it does affect the coefficients. Well, there's actually a statistic you can use to measure the multicollinearity in a multiple regression. It's called the variance inflation factor. I told you statistics people love their buzzwords. It's called VIF. If your VIF is greater than 5, you have severe multicollinearity. If it's between 1 and 5, you have moderate multicollinearity. If you have less than 1, you don't have to worry about multicollinearity. Again, I'll make a confession. In finance and investing, you're going to get that moderate multicollinearity show up over and over again. And if there is multicollinearity, here are some of the things you can try to do. If it's between a pair of your independent variables, you can try replacing one, perhaps, presumably the one that has less power in explaining your dependent variable, with something else, or removing it entirely. So I'll give you an example. One of the regressions we will talk about when we get to investing is the regression of PE ratios for companies against growth rates, payout ratios, and a measure of risk. Here's the problem you have. High growth companies tend to be high risk and pay out low dividends. So there's correlation across your independent variables. And if the correlation is high enough, here's what I'm going to do. If payout and risk are too highly correlated, I'm going to look at which one has more significance and remove the one that's less significant from my regression and run my regression with only two variables. The second is you can abandon multiple regressions entirely and run individual regression. In other words, I can take PE against growth, PE against payout. It's difficult to get a composite prediction, that's a trade-off, but you can run individual simple regressions. Or you can do nothing. Just use the multiple regression for predictions. Just don't read too much into the individual coefficients. So if you see the coefficient on risk is positive and you expect it to be negative, don't freak out. The multicollinearity can explain that. Now, in terms of prediction error from regressions, once you're done with the regression, one of the useful things to do is to take your prediction, how much your prediction is off from your actual value, and plot it against the expected value. So when you have prediction errors that are, so in a good regression, this is what your prediction errors should fall like. They basically should, there should be no pattern. This is a regression where the prediction values seem to get higher the higher the predicted value. In other words, the prediction error increases with the predicted value. That's called heteroskedasticity. And it's a problem with regressions when you have that. Again, the best way to fix this is to go back and revisit the data, see if you can alter, transform the variables, reduce the problem, but maybe you can't. You're saying, what do I do then? Well, there are other regression approaches that are more sophisticated and often carry a little more baggage in terms of statistical assumptions. First is what's called generalized least squares, GLS. In a GLS regression, you usually begin with an OLS regression, the traditional regression. Then you take what you find in the prediction errors and you use it to make the regression better. In other words, use the prediction error term to make your regression have better behaved prediction errors. You're actually using a feedback loop where you're saying, I'm screwed up. Let me take my screw up number and see if I can make my regression better. The output from a GLS regression resembles that of an OLS regression and can be used to make predictions. So if your statistics package allows you to do GLS regressions, all you're doing is opening that feedback loop, allowing your prediction errors to now become part of your prediction process. Another variant you can try is what's called weighted least squared regressions. In a traditional regression, each observation is weighted equally. But let's say you have a sample of big companies and small companies, and that you believe that what the big companies do should carry more resonance, more weight in your conclusions. In a weighted least squared regression, here's what you do. You weight the debt ratios or PE ratios of big companies more. So you use the market cap of these companies to weight the observations. So you're saying, why would I do that? Partly, as I said, because you think big companies should matter more in your regression, and partly because by doing that, you might remove some of the problems you had statistically, like heteroskedasticity. I've often found that when I run plain regressions across all US stocks, I have a lot of statistical issues. But if I weight based on market cap, those statistical issues become smaller. I'm not saying it's costless. You've given up some of the data strength when you do this. It's the weighted least squared regression. So let's summarize. When you have two variables or three variables or four variables, I think, if you're curious, it's always good to ask the question, do they move together? But remember, no matter how carefully you run a regression, when you make predictions from a regression, they're not facts, they're estimates. Those estimates will come with a standard error. Remember that best fit line that I showed you for the regression? Right below the slope, I should put a standard error and saying, this is how wrong I can be. If your R squared is low, that standard error can be large. Your prediction errors are also going to be larger. If your R squared is high, obviously the standard error shrinks. Second, regressions are run with data from the past. If you're using these regressions to make predictions for the future, one of the things you have to worry about is whether there have been changes in the structure that might cause your data to be different in the future. I'll give you a very simple example. I'm leery about using data prior to 2008 with US companies simply because I think 2008 was a structural shift for me, changed the way I thought about markets. So I might decide to be more careful about using data from 1970 to 80 to make predictions in 2020. Third, when you run a regression, you're going to use it for prediction. In other words, you're using X to predict Y. Remember, you've got to be able to observe X to be able to make the prediction. So often when you run regressions, you can run regressions that are called contemporaneous regressions. I can look at what earnings growth is at a company and show you that it's highly correlated with GDP growth. You're saying, this is good. I'm going to use GDP growth to predict how quickly earnings are going to grow. You know what the problem with that is? The GDP growth numbers don't come out till 3 or 4 months after the earnings growth numbers come out. So by the time you observe the GDP growth, you can't really act on it. So when you look at a regression, you got to make sure that the dependent variable is observable. Otherwise, you've run a neat looking regression, but it's purely post-mortem. You can't use it. And finally, in investing in finance, you want to act on your regressions. In other words, you don't run a regression just because you're curious. You want to take that regression and use it to get a predicted value. And you're hoping that over time, you're more right than wrong and that you can make money from it. Precision, stationarity, observability, actionability. Keep that in mind because in investing in finance, we have a very pragmatic end game. We're not looking at data for the sake of looking at data. We're looking at data because we want to use it to make better judgments as a company, better investments as investors. I hope you found the session useful and thank you very much for listening.